sacred institutions. Bedroom eyes, they call them in a bygone day.
Hello, and welcome to Physical Attraction, the show that explains physics, one chat-up line at a time.
But for corrupting others to a life of carnal pleasures and lewd designs. A man whose erotic desires and libertine practices are used to titillate the unsuspecting and would stoop to any depth.
Hello, and welcome to Physical Attraction, the show that explains physics, one chat-up line at a time. This week's episode, I can't resist. Superconductors. The life of an experimental physicist is not always an easy one. While the final papers they produce look very formal and correct, the day-to-day practice involves a lot of dubious, inexplicable, and sometimes just plain ridiculous results that come up. Things that don't make any sense. And 99.99999% of the time, the experimentalists will look at their apparatus, their incredibly complicated piece of experimental kit, and they'll realise that there's some problem with the setup or with the detector. They'll correct it, and then the ridiculous result just vanishes, to be replaced by something that makes a little bit more sense. Or, more often, another mistake that they need to correct. Not that the mistake is always recognised by the clever experimentalist. There was the famous case of the Canals on Venus. An astronomer called Percival Lowell spent years at his telescope mapping out these canals, drawing them up in intricate diagrams, and telling the world about his incredible discovery. If there were canals on Venus, then they must surely have been built by Venusian life. But it turns out that Lowell had been a little mistaken. He had the configuration of his telescope set up all wrong, and in fact, he may well have been mapping out the blood vessels in his own eye. So the next time you feel like all your work is futile and unappreciated, just consider the sad case of Percival Lowell, who ended up spending years drawing the inside of his own eye. And more recently too, the Opera experiment for measuring neutrinos a few years ago reported tentatively that they might have observed neutrinos travelling faster than the speed of light. This, if it were true, would have violated all known laws of physics and almost certainly won the experimentalists a Nobel Prize. But it turned out that, there were errors in the detector that meant that the faster-than-light neutrinos were actually slower than light. So experimentalists are used to things that don't make sense and that turn out to be experimental errors. Perhaps this was how Kammerling On felt. He was an experimentalist working at the physics of extremely low temperatures. At low temperatures, we tend to measure things on the Kelvin scale. That's the absolute scale of temperature. So 0 Kelvin corresponds to particles that have no kinetic energy at all. It's as cold as you can possibly get. And that's why it is an absolute scale of temperature, because it goes from absolute 0 all the way up to as high as you can possibly imagine. The units are the Celsius units, so 1 degree Kelvin is the same as 1 degree Celsius. On was looking at how substances behaved at these incredibly low temperatures. The huge triumph of his career had been in 1908. The work wasn't easy at all. The lab day started at 5 a.m, and by 7 p.m. he was almost ready to give up on his work. He was trying to cool helium down to the point where the gas would become a liquid. Now the only way you could do this at the time was by gradually reducing the pressure in the vat, allowing the gas to expand and expand and expand, and cool and cool and cool, all the while preventing heat from flowing in from the outside. So you had to do this in cycles that were very time-consuming and slow, and each cycle only got you a fraction lower in temperature. But the technique did work. He had been able to liquefy nitrogen, oxygen, and even hydrogen, cooling them down to only a few Kelvin, which is minus many hundreds of degrees in our usual systems of Celsius or Fahrenheit. But helium was an incredibly difficult nut to crack. It seemed that it liquefied at a much lower temperature. Having worked at it all day, On was almost ready to give up. Then a curious visitor from the chemistry department noticed what On had not. The vat underneath had been collecting liquid helium. Helium in its liquid form is a transparent liquid very close to air. Unlike water, which bends light, helium's refractive index is very close to 1, just like air, so it doesn't bend light nearly so much. On hadn't realised that he had been producing the world's first liquid helium for hours. And he also didn't realise that by cooling the helium down to around 1.5 Kelvin, he had achieved something truly remarkable. He had managed to defeat the universe. The background temperature of the universe, of the void of outer space containing nothing, is 2.73 Kelvin. On had created, in the lab, something colder than the empty void between galaxies. In the next few decades, after the liquefaction of these various gases had happened, extremely low temperatures fell out of fashion as an area of experimental research. After all, liquefying these gases was all very well, and experimental physicists, as much as rogue YouTube commenters, they all love to say, first. But there didn't seem to be much use for these incredibly cold temperatures. The atoms had virtually no energy, they were barely vibrating at all. Creating low temperatures was slow and difficult, and no one seemed able to solidify the gases that hadn't already been solidified. By 1911, On's lab at the University of Leiden was the only group of people regularly researching these incredibly low temperatures. But On was still interested in what happened to matter at the lowest temperatures humans could produce. Specifically, he was interested in what might happen to the conductivity of the matter, that is, how easily it passed through an electric current. In that era, they had a theory of how electric currents worked. Metals contained free electrons, charged particles that could somehow move throughout the metal. So if you applied an electrical field or an electrical force to the object, it would push the free electrons along. Electrical resistance is a measure of how easily an object can conduct electricity, how much force you require to push the electrons along. Metals have lots of free electrons, so their resistance is low. That was the model anyway. The idea of the time was that resistance was caused by the presence of atoms against this flow of electrons. The idea is that, as the electrical force pushes against the electrons, they're constantly bashing into atoms and giving them energy. This energy causes the atoms to vibrate, which is what we see as heat. And this explains ohmic heating, that is to say, when you pass a current through a wire, the wire heats up. The same principle is at play in your kettle when you pass a wire through the little metal thing at the bottom, which effectively heats up because it resists and boils your water so you can have some coffee. And it also explained thermistors. These were substances whose electrical resistance changes as a function of temperature. Generally, the hotter a substance was, the more electrical resistance it had. And this made perfect sense with this model of electrical conduction. Imagine electrons flowing through a substance where the atoms are barely moving at all. Well, then collisions will be rare. But if the substance is hot and the atoms are wildly vibrating, they're far more likely to crash into an electron and prevent the flow of electric current. But Lord Kelvin, the famous 19th century physicist and one of the last of what you'd call the truly classical physicists, he had a theory. He thought that if you cooled down a metal far enough, there would no longer be enough energy for there to be any free electrons in the metal that could carry the current. The electrons would instead all be bound into the atoms, without enough energy to escape from these atomic forces that pulled them in. So he predicted that if you cooled a substance down enough, the electrical resistance would suddenly spike to infinity. All of the electrons would be sucked back into their atoms and bound up there again, and they couldn't carry a current. It would be too cold for them to move and be free. So this was actually the idea that On and his student, Gilles Hulst, were investigating when they got to cooling down mercury to incredibly low temperatures. What they were expecting to find was that the resistance would spike to infinity when all of the electrons were sucked back into their atoms and couldn't carry the current anymore. But when they got to below 4.2 Kelvin, they noticed something weird. Instead of spiking to infinity, the resistance had suddenly dropped to zero. So On, the classic experimental physicist, assumed that there was a short circuit in his device. He was hunting around for the source of the short circuit. He was probably just about ready to scrap the experiment altogether when something strange happened. A lab assistant, tasked with keeping the temperature below 4.2 Kelvin, had dozed off, and the temperature accidentally rose slightly above 4.2 Kelvin, and suddenly the electrical resistance of mercury had reappeared. This showed that the resistance measuring kit wasn't broken. It could still measure a resistance. It was just that below the temperature of 4.2 Kelvin, the resistance seemed to drop to zero. Quite by accident, the team had discovered superconductivity. This was a bizarre finding. When you cooled down mercury to a cold enough temperature, the electrical resistance suddenly became 0. Not just some very small value, that you might expect if the atoms aren't vibrating very much, but precisely 0. It wasn't a straight line down towards 0, it was a sudden drop at this critical temperature. This meant that if you put a current into the superconducting loop, it would continue flowing forever. On tried it, and the current never seemed to diminish with time, as you'd expect when it lost energy to electrical resistance. And so he was able to show that, to within the best measurements they could make, the resistance was indeed 0. It wasn't a mistake. Not only was superconductivity the exact opposite of what On had expected to find, but he quickly realised that it had all kinds of exciting implications. For a start, a current that could flow forever without losing any energy. Could this mean transmission of power with no losses in the cables? Electrical current was already being transmitted across the Western world, but reducing these losses to 0 would save a huge amount of money. What's more, a superconducting wire where the current never ever diminished. It would act as a perfect store of electrical energy. Unlike batteries, which degrade and become unusable over time, if the resistance was truly 0, you could return to the superconductor in 1 billion years and find that same old current flowing through it. Energy could be captured and stored indefinitely. But there were even more exciting prospects. With no resistance, you could pass a huge current through the superconducting wire. The laws of electromagnetism tell us that when you pass a current through a coil of wire, it produces a magnetic field. With these superconductors, On thought, you could produce huge magnetic fields of incredible power. You could use them to levitate trains off the tracks and produce astonishing, almost frictionless accelerations. The transport system could be revolutionized. Perhaps in the future, these superconductors would allow people to lift incredible weights very efficiently. And every single power generator in the world operates on the following principle. You use something to spin a turbine that turns a coil of wire in a magnetic field. Turning the coil of wire in the magnetic field generates a voltage, which we use to generate power. This is the principle behind electrical generation. The difference between coal, nuclear, hydroelectric, etc. is really just how you get the turbine spinning. If superconductors and these powerful magnetic fields could be used in power plants, perhaps they could generate more electricity than ever before. In so many ways, this technology could change the world. And herein lies the beauty and the challenge and the fascination with superconductors. Because shortly afterwards, On noticed 2 things about this new phenomenon of superconductivity. If the magnetic field that the superconductors were in got too big, the resistance would suddenly reappear. The superconductivity would vanish as mysteriously as it arose. And if the temperature rose above that critical temperature, which was incredibly cold by anyone's standards, the resistance also returned. If, to use a superconductor, you'd need to cool it to a temperature close to absolute 0, and ensure that the magnetic field wasn't too high, then all of these miraculous applications would be much more limited. On started to search around for other materials that might exhibit this same property, but conveniently at a higher temperature and for stronger magnetic fields. And in some ways, you could end the story of superconductivity right there, because despite more than a century of effort now, we haven't managed to find that miracle substance that we've dreamed of for so long, a room temperature superconductor, which would revolutionize so many aspects of the modern world. We've found superconductivity in all kinds of different materials, at a variety of different temperatures and magnetic fields, but we've never found that elusive superconductor that works at room temperature. So in some ways you could end the story there, but as ever with physics it's not quite that simple. In the next part of this episode, I'll talk about the developments in superconductivity in the materials that we use, the technological applications that have been found, and the theoretical understanding we now have of this mysterious experimental phenomenon. But first, this week's physics-based chat-up line. You make me feel like a superconductor at 4 Kelvin. I can't resist. Meow. And on the same theme, a superconductor walks into a bar. The bartender says, "Get out, we don't serve your kind here." the superconductor leaves without resistance. With these lines, you're sure to be as cool as a cupcake. Okay, enough of this fun. Back to the science of superconductors. Like many weird things in physics, it was generally considered that superconductivity was probably a consequence of quantum mechanics and quantum weirdness. It wasn't just like having a substance with no electrical resistance, because scientists also noticed that superconductors didn't like having magnetic fields inside them. There's something called the Meissner effect, which means that when a material becomes superconducting, it expels almost all of the magnetic field lines inside itself. Magnetic forces don't operate inside the superconductor, but only outside, and in an incredibly thin layer on the surface of the material. This can't be explained with classical, non-quantum physics. So we've talked about the experimental discovery of superconductivity, and how the experimentalists began to hunt for more substances that would exhibit this strange property. But it was up to the theorists to explain how superconductivity actually worked. What was the mechanism that let the resistance drop to zero? And they sort of did, until the experimentalists found a new type of superconductor, just to make things really difficult. Such is life. First, it was discovered that superconductivity was really a little bit like a phase transition. In our day-to-day lives, we're familiar with phase transitions of some kinds, like for example boiling or freezing water. Both of these are processes where, at a certain temperature, the behaviour of the system can change on a macroscopic scale. Water goes from being a liquid to a solid crystal, or a gas depending on whether you're boiling or freezing it. We say that the water has changed from a liquid phase into a solid or gaseous phase. Superconductivity can be understood in the same way. Below the transition temperature, the phase of the material completely changes, and it becomes superconducting with very different properties. Landau and Ginzburg managed to find an equation that described the superconductors in terms of the energy of the system, which let them make some theoretical predictions about how the superconductors should behave. Now this was similar to how other magnetic materials, like permanent magnets, had been described in the past. You can write down equations that tell you how energy is distributed in the magnets, and once you know that, it lets you make predictions about how the magnet will behave. They had an equation, but they still didn't have a microphysical explanation for what was physically going on. They didn't know what the electrons were doing. They could tell you where the energy would be in the system as a whole, but they couldn't tell you what the electrons were doing. What were the electrons in a superconducting material up to? Lord Kelvin's idea that at super low temperatures they would freeze into atoms was clearly incorrect. If anything, it seemed like they became permanently free, capable of moving without any inhibition at all. But if this freezing wasn't what was happening to the electrons at cold temperatures, what was? So this gets quite complicated, but I'm going to try and explain it as simply as I can. It's something called BCS theory, named after Bardeen, Cooper and Schrieffer who came up with it. Here's the basic idea. We can imagine how metals work as a lattice, a grid of atoms regularly repeated, which has electrons in it. An electron moving through the conductor will attract nearby positive charges in the lattice. This is because the electron has negative charge, and so it attracts positive charges. So you should imagine as the electron is tripping through the superconductor, it will be pulling the positive charges towards it. But this pulls on the lattice structure and causes it to deform. The deformation of the lattice causes another electron with opposite spin to move into the area where the electron is. So it pulls positive charges close to the first electron, and this dense positive charge pulls in another electron. And then the two electrons become correlated. This is a quantum mechanics idea. All that matters is the idea that the electrons are now linked together. Now imagine this happening in lots of places in the superconductor. Because there are lots of such electron pairs in a superconductor, these pairs overlap very strongly. In this state, where the overlap between electron pairs is strong, you can't change one pair without changing all of the others. Thus, the energy required to break apart any single pair of electrons is related to the energy required to break all of the pairs. What this does is that it means that the tiny energy you usually get when the electrons are paired together actually becomes a much larger energy, the energy required to break up all the pairs of electrons. Normally you don't notice this effect. This is because the temperature is quite high, and so the atoms in the conductor are vibrating. They have a lot of energy. When they have a lot of energy, they can bash into a pair and break all of the pairs, and so you don't notice this quantum effect. But in a superconductor, the atoms are at very low temperatures. Bashing into an electron pair isn't enough to break them apart. This means that the pairs stay stuck together, and they resist all the kicks from the lattice that try to break them apart. And because they're resisting the kicks, the electron flow as a whole, the current through the superconductor, will not experience resistance. That, broadly, is how a superconductor works. These pairs are formed, they become correlated so that they overlap with each other. You need a lot of energy to break apart the pairs, and below a certain temperature, the lattice doesn't have enough energy to break them apart, so they can flow unimpeded. So maybe if you're feeling a little bit cute, you could get a physics-based chatted line out of Cooper pairs. The bond between us is a lot more difficult to break than you'd think. Of course, you can probably now see why superconductivity happens in some materials and not others, and at different critical temperatures. It's all to do with this lattice structure, which varies from substance to substance, and how it gets deformed. But the BCS theory that was described above was actually pretty depressing for researchers into superconductivity. It implied that even if you had a really good lattice structure, superconductors couldn't exist above 30 Kelvin, which is minus 243 degrees Celsius. In other words, the BCS theory said that it was unlikely that we'd ever find a truly useful room temperature superconductor. So there you go. You know how superconductors work. Or at least you know how conventional superconductors work. The story's not over yet. Did you think it would be that easy? Unconventional, high-temperature superconductors were discovered in 1986. We found them in strange materials called cuprates, which contain copper in their lattices. Often, you need quite weird arrangements of exotic atoms in the lattice to get high-temperature superconductivity to work. So one of the most famous examples is YbCO, which is yttrium barium copper oxide. In other words, it contains two elements that most people have probably never heard of. I certainly hadn't heard of yttrium or barium before I looked into this stuff. Explaining high-temperature superconductivity is still an unsolved problem in theoretical physics, although people do have theories about it. But a theoretical understanding of this is super important, because if we have the theory, we might be able to predict what substances will make good high-temperature superconductors. And, even better, we might be able to see if there's another limit. Maybe it will turn out that it's possible to have a room temperature superconductor, at which point we should direct lots of investment and lots of research efforts in that direction. So how high temperature is high temperature? The best one to date becomes superconducting at around 130 Kelvin, which is still minus 140 degrees Celsius. In other words, it's incredibly cold. But one crucial thing about the high temperature superconductors is that it's warmer than liquid nitrogen, which we can produce fairly easily in the industrial scale, which means that high temperature superconductors have found some uses. The other aspect of high temperature superconductors is that the colder they get, the more of a magnetic field they can tolerate. So if you have a 130 Kelvin superconductor that's actually operating at 20 Kelvin rather than 130, it will be able to have a bigger magnetic field inside it. It sort of seems like either you have a high temperature and a low field, or a low temperature and a high field. But it tends to be that the best superconductors that can operate at the highest temperatures also have the highest maximum magnetic field that you can have flowing through them. So you can dip one of these things in liquid nitrogen, get it pretty cold, and you can produce a big magnetic field. For example, superconducting magnets are used to produce the big magnetic fields at the Large Hadron Collider, which bends those particles into flying around in circles and smashing into each other. Superconducting magnets are used in the experimental fusion reactor, JET, in Oxfordshire, and they will be used at the new one, ITER, in France, when it's completed, whenever they get around to finishing that. An episode on nuclear fusion shortly, I think. They're also used in MRI and NMR scanners, which you may have had some experience with in a medical environment. And superconducting magnets have been used to levitate frogs, in a display which won the Ig Nobel Prize a few years ago. Superconductivity is still a very active area of research. Just in 2014, some German physicists discovered they could make a superconductor by bombarding a substance with lasers. No need to cool it down at all. Unfortunately, the material only remains superconducting for a few milliseconds, so the effect isn't really useful yet, but it's still being investigated. We all know that a room temperature superconductor, or one that can work at a decent range of temperatures, could change the world. Change the way we think about transporting and storing energy, how we think about transporting people and objects, and how we generate our power. That marvellous, mad experimental result from 1911 continues to confound, mystify, and excite physicists to this day. There is no question that superconductors are still ridiculously cool. Thanks for listening to this episode of Physical Attraction. If you've enjoyed it, please tell as many people as possible about it. Think about yourself as being an electron in part of a Cooper pair. You've got to entangle them into the web of the show. And of course, the more listeners we have, the more likely it is that I become incredibly famous and wealthy. And when that happens, I'll give you a little kickback for helping us. You can follow the show on Twitter at PhysicsPod. You can visit us online at www.physicspodcast.com. Either one of those is a great place for you to send any questions you have about physics, about the show, and it will feature in a future upcoming eventual listener questions episode. We'll be back soon. Until then, be kind to each other.